Okay. So just a quick reminder, recap of where we left off on Tuesday. So Tuesday we introduced linear programs, and so we talked about a language for encoding problems as linear programs. We did a toy example. We also did many real examples: max flow, min, cos flow, fitting a line, learning linear classifiers. Here's the toy example from last time. Actually, I tweaked it a little bit. Last time this 4 was a 2 and this 2 was a 1. I wanted to break symmetry, so I modified it slightly, but the picture's almost the same. I really just took one of the constraints and kind of lifted it up a little bit. And so this intersection of 4 half planes, you want to find the best point, what's best, maximize the sum of the 2 coordinates, just like on Tuesday. That corresponds to moving northeast as far as possible. And so here, last time it was 1/3, 1/3. With the tweaked constraint, the new optimal is 3/7, 2/7. So you can check that this point 3/7, 2/7 satisfies both of these constraints with equality, and it achieves a objective function value of 5/7. Okay? And so in general, what is a linear program? What's the recipe? Well, there are decision variables, like here x1 and x2. There are linear constraints, linear meaning that each decision variable can't be multiplied against anything else, nor can you apply any nonlinear function to it. You can just multiply it by a constant and then add up a bunch of those terms. The constraints are allowed to be either inequalities or equalities. Remember, that was one of the points of linear programs. If you only have equalities, you can use Gaussian elimination to look for solutions. But lots of problems, like all of the ones we saw on Tuesday, naturally have inequalities, so those are also allowed. Okay? So any questions about that? Any questions about where we left off on Tuesday? So the plan for today is we're going to start talking about linear programming duality. So last lecture, oh yeah, question?
Can you explain why exactly maximizing x1 plus x2 is going in the direction of the vector 1, 1? Because it seems like I could draw a different graph which does not have lines, in which that is not the case.
Which does not have lines.
Where I draw like some concave weird thing. Like why?
So I would again think about the level sets of the objective function. Okay, so.
Right, so my question is why is it the vector 1?
Well, so if you prefer, think about it this way. Think about the subset of solutions. Just think about the subset of the plane that has a given value of x1 plus x2. Like x1 plus x2 equal 1. Okay, so that's going to be a line, 45-degree angle, going from northwest to southeast. Right, so if I just look at, so basically, the plane gets chopped up into these parallel lines, each one corresponding to a particular objective function value. And the objective function value is getting bigger as I go northeast. So I mean, it's almost just, we're really just trying to maximize the dot product of, x1 comma x2 with the vector 1 comma 1.
I guess that's the part that I don't understand.
So that's just the definition. What is x1? Think of x1 plus x2 as 1, 1 dot product x1, x2. It's the same thing, right? Okay. Okay. Good. So, the topic for today's lecture is linear programming duality. And LP duality, honestly, it's really the heart and soul of this entire course of CS261. We'll talk about it all lecture today. We'll talk about it some more on Tuesday. I want to spend some quality time with LP duality so that you have a sense to really kind of absorb it at more than just a superficial level. And at some point it'll be clear that actually all of the last 3 weeks I was also teaching you about LP duality. And that won't be obvious immediately, but it'll become somewhat clear through the lecture today. Okay? So to start the story, let's just look at this toy example. So we solved it by inspection, right? It's just in the plane, and it's a simple one. So we just said, oh, let's move as far this way as possible. That's the right point. But as we scale the number of decision variables, the number of dimensions, we're not just going to be able to eyeball some picture. So how can we get a handle on what the optimal might be? And so, stopping shy of actually computing it, let's actually just think about how would we convince somebody so given a feasible solution, what would convince you that it actually is an optimal solution? Just like when we talked about flows, what would convince you that a flow is actually maximum? What would convince you that a matching is actually maximum cardinality or minimum cost? So let's think about this. Let's suppose we didn't know what the optimum was. We were just staring at this linear program. We wanted to understand upper bounds on how big the optimal solution could possibly be. So So one kind of very trivial upper bound would be an upper bound of 2. How can we derive that? Well, if you have a feasible point, okay, x1, x2, so feasible meaning satisfying all 4 of these inequalities, and we look at the objective function value, i.e. x1 plus x2, well, certainly that's bounded above by 4x1 plus x2. Actually, I'm using something here. What am I using? x1's non-negative, right? So if x1 was negative, this would be wrong, okay? But with x1 non-negative, a bigger coefficient only makes it a bigger quantity. And so this is by the first constraint. And now using the third constraint, just sort of by definition of feasible, we find that it can't be bigger than 2, okay? So this is kind of an obvious argument about whatever the optimal solution to this linear program is, it's not going to be bigger than 2. Okay? Everyone clear? All right. So hopefully you found that sort of trivial. Actually, if you think about it, this was really stupid. It'd be better to use the last constraint instead. That gives us an upper bound of 1 on the optimal solution. Right? So this is a tighter upper bound, better upper bound. This is a stronger statement than the last one. Okay? But actually, if you think about it, there's no reason to just use a single constraint to derive upper bounds on the optimal solution. We should feel free to blend them as it suits our purposes. So to see what I mean, notice that I can write x1, x2 as a convex combination of the 2 constraints. So I take 1/7 times 4x1 plus x2 plus 3/7 times x1 plus 2x1. This holds with equality. Okay, it's just algebra. I actually only need an inequality, like in the first 2 cases, but I happen to have equality. Okay? So again, this is just algebra. And now, because, assuming that x1 and x2 are feasible, by the third constraint, we know this number cannot be bigger than 2, no matter what. By the last constraint, and feasibility, we know this cannot be bigger than 1. So that gives us an upper bound on 5/7. Okay? So this, you should find a quick and convincing proof that whatever the optimal solution to this linear programming is, the objective function value is definitely not bigger than 5/7. Okay? All right. Now in this particular case, we actually know this is a tight upper bound because we know there's a feasible solution to this linear program, 3/7, 2/7, that actually does attain this upper bound, that actually has objective function value as high as 5/7. So clearly we're not going to prove any better upper bound. Okay? This is the best as it gets. So any questions about that? All right. So that's more or less duality in a nutshell. But so let me develop it more generally. Right? So if you think about it, nothing about this argument uses the fact that we're in the plane, or uses the fact that there's only a very small number of constraints. We're just saying, oh, if you can just use suitable linear combinations of constraints to derive upper bounds on the optimal objective function value. So what does that look like in general? Here's what it looks like in general. So suppose we have not just 2 decision variables and 4 constraints, but an arbitrary number. So consider a linear program of the following form, and I'll call this P for reasons that will become obvious. So maximize a linear combination of the decision variables. Decision variables are x1 through xn. Then we have our linear constraints. J equal 1 to n. And so let me just go with, for the moment, linear programs that have the same form as the one up there, where we're maximizing, we have inequalities, and we have non-negativity constraints. Okay, we'll talk about other forms in a second. So that's what one linear constraint looks like. In general, we have m of them. And then again, let's think about scenarios where all of the decision variables have to be non-negative. Okay? Now, we talked a little bit on Tuesday about how, there's a lot of different forms of linear programs, but they're all equivalent. It's easy to go back between one and another. If you have a minimization linear program, you can just multiply the objective coefficients by -1 to turn it into maximization. If you have inequalities going the opposite direction, you can flip them by multiplying by -1. And if you have equations, you can simulate those with two inequalities, okay, going both directions. So there's a sense in which it's basically without loss of generality to talk about this form, but still I'll talk about other forms a little bit later. Okay? So suppose so now, right, so just in this generality, there's no way to eyeball anything and just sort of deduce what the optimal solution is. So let's again take a step back and say, well, what if we at least wanted to just convince ourselves of legitimate upper bounds on what the optimal solution could be? Okay. So let's just follow the previous approach. So suppose, all right, so what were we doing in these arguments? Okay, we were taking a multiple of the first constraint plus a multiple of the second constraint. Okay, and we were playing around with what multiple we should use. So we're going to have y1 through ym. These are just going to be those multipliers on the constraints. Okay, so because there's m constraints, there's going to be m multipliers. Okay. So suppose you have non-negative multipliers that satisfy. So what was really driving the argument here, right? So let's look at those first inequalities. What was important was that your convex combination dominated the objective function coefficient by coefficient. Okay? So 4 and 1 or at least 1 and 1. 1 and 2 or at least 1 and 1. That's what we need. So in general, what does it mean that your linear combinations dominate the objective, dominate the CJs? Well, what it means is that for every coefficient of the objective function, so of which there's n, so for all I equal j equal 1 up to n, it should be the case that if I look at the coefficient that I get on a given decision variable, which in general is written like this, this should dominate that coefficient of the objective. Okay? So we're going to call this star. So for example, in the first argument up there, we took y1 equal to 1 and y2 equal to 0. Okay? And it was the case that, for example, for the first decision variable, 4 was bigger than 1. And in the second decision variable, 1 was bigger than 1. In the second argument, we took y1 equal to 0 and y2 equal to 1. Okay? And again, this was satisfied. And then in the final argument, we took y1 equal to 1/7, y2 equal to 3/7, and actually this wound up holding with equality for both j equal 1 and 2 in that case. Okay? All right. So suppose this is true. From this, we can extract an upper bound on how big the optimal solution to our linear program could possibly be. And it's just a generalization of this argument here. Okay? So suppose y are non-negative and satisfies star. Then for all feasible solutions x to our linear program P, we can write as follows. We can write the following. This is the objective function value of x by definition. Remember, we want an upper bound on the optimal objective function value. So I'm taking your favorite feasible solution. I'm going to upper bound its objective function value. Here it is. Okay? So now we just follow our nose, right? So what do we know? What do these y satisfy? Well, if we take the non-negative linear combination of the constraints as specified by the y's, it dominates the c's. It's at least as big as the c's. So what that means, and again, this is just corresponding to these two lines here. It means I can replace Cj by the left-hand side of star. Okay, that's what star means. Again, I'm using here that each of the x's is non-negative. So boosting its coefficient only gives me a bigger number. Okay? So Cj times sum over I equals 1 to m yi aij. Okay? Ah, good. Oh, sorry about that. Okay, so this is star plus x non-negative. All right, so whenever you have just a general rule, whenever you have a double summation and you don't know how to interpret it, just reverse the order of summation and see if you get something you can make use of. So we'll do that here. So instead of summing over j and then I, we sum over I and then j. So let's yank out the part that doesn't depend on j. So we get a yi there, and then a sum over j equal 1 to n of aij xj. Okay? So that's just algebra, rearranging. Well, this is something we know something about. X is a feasible solution. It satisfies every constraint of the linear program P. In particular, this linear combination has to be at most B sub I. Okay? By feasibility. And so this is using that x is feasible, and we're also, again, using non-negativity, this time that the y's are non-negative. Okay? So that is the natural generalization of these simple upper bounds for our toy example. And so again, what is the upshot? The upshot is that for all y, again, these are m vectors, such that star holds, the optimal solution, the optimal objective function value of our linear program is bounded above by the dot product of B with I. Okay? And so if you think about it, you know, this right-hand side is exactly the upper bounds we were getting in our toy example. When we took, so maybe you don't remember, but so B1 was 2, B2 was 1, right? The right-hand side of our linear program was 2 and then 1. So when we took y1 equal to 1, y2 equals 0, we got an upper bound of 2. When we talk y1 equal to 0, y2 equal to 1, we got an upper bound of 1. And then the smarter convex combination, this became 5/7. Okay? Now, in my experience, by the time computer science students make it to my classes, they've totally forgotten any linear algebra they may have once known. I don't know how many of you that applies to. But when you're talking about linear programming and duality, it's really helpful to also be able to think of linear programs in terms of matrices and vectors. Okay? So let me just point out what's the vector / matrix version of everything we wrote on the board. Right, so for our initial linear program, we can think of the objective function as maximizing C transpose X. Here C and X are both n vectors, so we're just taking the dot product or the inner product of two n vectors. This system of linear inequalities we might write succinctly as AX at most B. So what does this mean? So X here, as you know, is an n vector. A, so the rows of capital A correspond to the constraints. Okay, so the first row of A are just the coefficients A1j for all j. So there's m constraints, so A has m rows, and then there's n columns in one-to-one correspondence with the variables. And then B here is going to be an m vector. Notice that there are m entries, one for each constraint. Okay? So this is an m vector, that's an n vector, and A is m by n. Okay. Non-negativity we might write succinctly by x non-negative. Notice these inequalities, they refer to vectors, so we always mean it point-wise, component by component. One should be at most the other. So similarly, when we talked about our non-negative linear combinations of the constraints of this linear program, we're talking about vectors y, now of length m, because they're in one-to-one correspondence with the constraints, one multiplier per constraint. And how would we write this? This is a little tricky. So clearly we're writing at least c on the right-hand side. And presumably there should be a capital A and there should be a y. So what is that exactly? Good. As many of you said, A transpose Y. Why A transpose? Well, here we're looking at the dot product of X with rows of the matrix. Okay, if you think about each of these left-hand sides, it's the dot product of X and a row of the matrix. If you stare at this and you realize you're summing over I rather than J, oh, now you're taking the dot products of Y with columns of the matrix. Okay? Which actually, if you think about it, it makes, for things to type check, that has to be true, right? Because Y is an M vector, A is M rows by N columns, so you better be dot product Y with columns of capital A. That's all that would make sense. So that's the same thing as just doing A transpose Y, okay? This derivation, I think, actually looks somewhat less obscure when you switch to this vector matrix notation. All we're saying here is that C transpose X is at most A transpose Y transpose C. Right, so this is using that C is dominated component by component by A transpose Y. Remember, that's just our condition star. This reversal of summations is really just distributing the transpose and then using associativity. So this is equal to Y transpose parentheses AX. I screwed this up again, didn't I? Sorry about that. It should be X. AX. And then the final step is just using that B dominates AX component by component and Y is non-negative. So this is the most Y transpose B. Okay? So that's why you should get familiar with, or sort of just page back in, matrix vector multiplication, because you can replace this messy board of sums with just actually a very elegant derivation in terms of the matrices and the vectors, okay, which I think is much more transparent. Okay. But again, this is the upshot. Okay? So if you ever have a non-negative vector Y such that A transpose Y is at least C, so these non-negative linear combinations dominate the coefficients, then you extract from it an upper bound on how big the optimal solution could possibly be. What is that upper bound? It is just the right-hand side, B, that vector, transposed with your non-negative linear combination coefficients, sort of dot product with a Y. Okay? So any questions about that derivation? So this is a generic way of proving to you that the optimal solution of a linear program cannot be too big. Okay? Now, if you recall our toy example, we had some upper bounds initially, and they kind of sucked, actually. Right? There were much better upper bounds than the first ones we tried. So some of these upper bounds are going to be good, or some of these upper bounds are not going to be good. Hopefully some of them will be good. Now, from our perspective, which upper bound are we most interested in? Well, obviously the tightest upper bound, right? We want the strongest information possible about how big our linear program solution could be. So amongst all upper bounds, you can derive in this way by choosing multipliers y's subject to the constraints. Among all of those, really the one we're interested in is the one that gives us the tightest upper bound, i.e. that makes this right-hand side as small as possible. Okay? That is the most interesting upper bound, this being as small as possible. So here's the key point. The tightest upper bound of this type, by of this type I mean you choose non-negative y's subject to star, The tightest upper bound of this type is itself a linear program. Okay. What does the linear program look like? Just, we sort of already know this, but just to make sure, make it concrete. You sum BI, YI. Why do you minimize this? Because this is our upper bound. The best upper bound is the smallest one. We're searching for the best, so we're searching for the smallest. Subject 2, so we had Y1 through YM non-negative, and then we have star. Okay? So let me just actually write star. Because hopefully it's evident, you know, these are linear constraints. All right? So this is called the dual linear program. Okay? So D. And again, in matrix notation, what is this? You want to minimize Y, let's do B transpose Y. Subject to A transpose Y dominates C, and Y non-negative. Okay? So to review, consider any linear program of the form on the upper left. Max C transpose X, subject to AX at most B, and X non-negative. Every linear program of that form has what's called a dual linear program. What the dual linear program is it minimizes B transpose Y, subject to A transpose Y at least C, non-negative linear combinations to dominate the original objective, and again, Y non-negative. Okay? So constraints and variables have reversed roles. The right-hand side has become the objective and vice versa. And the constraint matrix gets transposed. Okay? So this is the dual LP of a linear program of this form. And by construction, the optimal objective function value of P of the so-called primal linear program in the upper left is at most the optimal objective function value of the dual. Why? By definition, what is the dual? What does it mean? Feasible solutions to the dual linear program correspond to valid upper bounds on the best possible objective of the primal. That is, every feasible dual solution gives you an upper bound on the value of every primal feasible solution. So that's true in particular for the best of all of the duals and the best of all of the primal solutions. Okay? So we don't know whether this holds with equality or not, but just by construction, by the definition of the dual linear program, it will always be the case that the objective function value of the minimization program is at least that of the maximization part of the primal dual pair. Okay? So just as a sanity check for our toy example, the dual is going to be minimize 2y1 plus y2. I guess I erased the original one. So the original one was max x1 plus x2, subject to 4x1 plus x2 at most 2, x1 plus 2x2 at most 1, x1, x2 non-negative. So what's the dual? Well, the objective function of the dual corresponds to the right-hand side of the primal. So the right-hand side here is 2, 1. So we see the 2, 1 in the objective function here. So for the same, okay, so we also know this is going to be a greater than or equal to, right? A transpose Y is at least C, component-wise. So the right-hand side of the dual is going to be the objective from the primal. So the objective function coefficients here are 1, 1. So we're expecting two constraints that both have 1 on the right-hand side. okay? So over here, we're going to have some y1s and y2s. We need to understand what their coefficients are. Their coefficients are provided by the transpose of the original constraint matrix. So the coefficients here are going to correspond to the coefficients of x1 in the two constraints, okay? So this is the first column in A, in the original constraint matrix. That's going to become the first row in the dual, okay? Sorry, there. So it's going to be this 4 and this 1, excuse me. So 4y1 plus y2 is at least 1, because the coefficients of x1 are 4 and 1. The coefficients of x2 are 1 and 2. So that's going to give us coefficients of 1 and 2 here. Okay? And then we'll have y1 and y2 non-negative. Okay? So this is just saying all of the simple upper bounds of the type that we discussed for this particular linear program. We, in fact, solved it optimally, right? Because we exhibited a solution to this linear program with value 5/7. That was 3/7, 2/7. We also exhibited a feasible solution to this linear program with value 5/7. That was 1/7, 3/7. And we know, remember, the optimal solution here can only be bigger than the optimal solution here. So I exhibited for you a feasible solution of each so that both have value 5/7. Both of them have to be optimal, okay? So nothing can be higher than 5/7 as the primal, because that would contradict the fact that we have a dual solution with value 5/7, and conversely, okay? All right, so questions about that. Next up is an example. So I want to make this a little more concrete by applying it to maximum flow. Questions? So far, so good? All right, so I've tried to make this somewhat concrete with our toy example, but let's actually apply this theory to a kind of real example and see what we learn. So I want to return to the maximum flow problem. Now on Tuesday, we observed that the maximum flow problem really by definition translates easily to a linear program with constraints corresponding to conservation and capacity constraints. Today, I'm actually going to work with a different linear program than the one I showed you Tuesday. The linear program is going to be bigger, but it's going to be simpler, and therefore it'll be easier to take the dual. Okay? The idea is rather than working with just flows on edges, we're going to work explicitly with a path decomposition with flows on paths. So alternative LP So before we had a decision variable for each edge. Now we're going to have a decision variable for every ST path. Okay? So we're going to have decision variables indexed by this set script P, indexed by ST paths. Now mind you, a graph can have an awful lot of ST paths, an exponential number in fact. But we're not going to solve this linear program. We're not going to feed it into a linear programming solver. We're just going to use this as a thought experiment. We're going to use it for analysis only, okay? All right. So what do? So we just want to send as much flow as possible. So we enumerate over every possible ST path flow could be sent on. We look at how much flow FP is sent on that particular path, and we sum up over all the paths. So that's the flow value. And now what's nice about this path formulation is conservation constraints are just handled automatically, right? Because if you have a path, conservation constraints are satisfied. If you superimpose a bunch, you still have conservation. I still do need the capacity constraints, though. I still have to encode that. So we're going to have at most capacity for every edge. Shouldn't be surprised to see that. So what goes on the left-hand side? Well, it should be that the total amount of flow on edge E, no matter how it got there, should be at most the capacity. Okay? So a given edge is part of many different ST paths in general. So we have to enumerate over all the ST paths that include this edge and make sure their total flow obeys the capacity constraint. So we write sum over all paths, ST paths, for which this particular edge E belongs to it. Okay? So this is just the total flow on E. And then, of course, flow should be non-negative. Okay? I hope it's at least plausible that this is, for all practical purposes, a equivalent LP formulation to what we had Tuesday. So in exercise set number 4, I ask you to think about that carefully, that the optimal solution is exactly the same value for either of the two linear programs that we've seen. Okay? And again, the idea is really here we're just working with path decompositions in the sense of problem 1, which you just completed, instead of with the flows on edges themselves. So what I want to do next is I want to see what the dual linear program is to this linear program. Notice this is in the form that we've been talking about, right? We're maximizing C transpose X. So let's see. So let me actually write this out. So we're maximizing C transpose X, but let me write that as 1 transpose F. So F will be the variables here. Notice every variable has coefficient 1 in the objective. So this is just the vector of all 1s. And the constraints have the form AF and most U. We'll talk about what capital A is in a second, but they're inequality constraints going the right direction. And then we have non-negative variables. Okay? So this is exactly the type of linear program that we've been talking about this lecture. So we know how to take the dual. Yeah? Now, often the hardest thing about taking duals, or at least understanding what you're actually doing when you're taking duals, is just actually understanding the meaning of transposing the constraint matrix. Okay? That's usually what's kind of, initially unclear, but then you think about it a little while, and then you're like, oh, okay, now I get what this dual is doing. So let me show you, just for example, in this particular program. So what is this matrix capital A? Okay, the constraint matrix here. So what do the rows correspond to? Remember, rows correspond to constraints. So we have 1 row per what? Per edge. We have these capacity constraints, 1 per edge. So the rows here are indexed by edges. What are the columns indexed by? So the columns are so the rows correspond to constraints. The columns correspond to decision variables. We have a decision variable for each path. Okay. So those are the dimensions of our constraint matrix. What is an entry of the constraint matrix? Well, the constraint matrix entries are just the coefficients of your decision variables in your constraints. We've got actually quite simple constraints. Okay? In fact, each entry of capital A can take on only one of 2 values, 0 or 1. Right? Whenever a decision variable appears, it's with a coefficient of 1. And so when does that happen? Whoops, I shouldn't, not AIJ. Let me write AEP. Okay, so the row corresponding to E, the column corresponding to P. When is this going to be equal to 1? For which pairs of edges and paths will the corresponding entry of this constraint matrix be 1? Yeah, E is on P, exactly. Why is that true? We'll fix a row. So what we're asking is, let's fix a row. How many of the which decision variables actually show up in this particular constraint? Right? So anything that doesn't show up has a 0, anything which does show up has a 1. The things which shows up are just the paths that contain this particular edge. So as we go through a row here, we get a 0 whenever the path doesn't have the edge. We get a 1 whenever the path does have the edge. because those are the variables that appear. All right? Questions about that? If you get that, then we're ready to take and interpret the dual. All right. So, dual. So what's the recipe? Okay. Well, for each constraint of the primal linear program, we have a variable in the dual, right? Multipliers for the constraints. So rather than y, I'm going to call them L. I'll explain why in a second. So one variable LE for each edge. Okay? So one dual variable for each constraint. And again, I think the easiest thing to do here is to actually take the dual using the matrix notation and then sort of unpack what it means as far as, more primitive objects. So we have a max over here that becomes a min. The new objective function is the old right-hand side. Okay, so it's going to be minimize. So the dual variables are L, so L transpose U. The constraint matrix gets transposed. So this is an A transpose L. The new right-hand side is the old objective function. Okay, so this is going to be at least 1 component-wise. And then we have non-negativity constraints. Okay? So is everyone cool with what I did on the matrix side? Okay, so this is exactly the recipe that I told you before. All right, so let's unpack this in terms of edges and paths and so on. So min L transpose U, remember the dual variables are indexed by edges. So this is going to be a sum over the edges of the capacity of the edge. This is fixed, this is a constant, times the dual variable, L sub E. So that's the objective. Obviously down here we have the L's are non-negative. So let's try to understand what this means, okay? So first, just let's make sure we get it type checked correctly. So in the dual, we're going to have one constraint for each primal that we had, for each decision variable that we had in the primal. So in the primal, we have a decision variable for every ST path. So over here, we're going to have a constraint for every ST path. So let me write for all ST paths, P and P. Okay? So we're going to have a family of constraints indexed by the path. We know that they're going to be greater than or equal to constraints. And we know that the right-hand side is 1. So the question then is, what does it mean to talk about a particular constraint of A transpose? What does this look like? Okay, so we want to know what the rows of A transpose look like, or equivalently, what do the columns of A look like? So let's go back to A. So what's a column? So column is some fixed path P. So now imagine we just scan up a particular column. Okay, so the path is fixed. We're now scanning over the edges. Okay, remember the rows are indexed by edges. We see a 0 whenever the edge that we're looking at is not part of this path. We see a 1 for any row where that edge is part of this path. So in other words, the column corresponding to the path P is just the characteristic vector of the edges in the path. So 1 for edges in the path is 0 for edges out of the path. Okay? So that's the column of A, that's the row corresponding to the constraint of A transpose, okay, in the dual. So what does it mean to take the inner product of a column of capital A with L? Well, for any edges not in the path, they have a coefficient of 0, so they disappear. And then the other ones have a coefficient of 1. So what we get here is just sum over the edges in this fixed path P of L sub E. Okay? So that is the dual of this max flow linear program. Any questions about that? Next, I mean, it's not supposed to have meaning for you yet. I'm going to give you that next. Okay? But are you okay with just the syntactic transformation? Do you agree this conforms to what I told you before? Okay. All right. So one cool thing is that natural problems, when you take their duals, you often get something which is meaningful in its own right. Okay? And that turns out to be the case with maximum flow as well. So, how should you think about this dual? Well, so one way, just kind of if you want sort of a physical interpretation, the decision variables, I called them L. Why did I call them L? I did that to suggest that they're sort of like a length. Okay? So we're actually computing lengths for the edges of this graph. With that interpretation, there's a very succinct description of these constraints. Do you see what it is? So if this inequality holds for every path, then it also holds for the shortest path with respect to these edge lengths that we computed. Okay? So this constraint boils down to saying compute non-negative lengths on the edges so that if you compute a shortest path, it's going to have length at least 1. All right? So that's what you're doing. Somehow you're pushing S and T sufficiently far apart. Shortest path distance at least 1 apart. So that's a physical interpretation of the constraints. So then what's sort of up with the objective? Well, if you like, think about a capacity as the width of a pipe. Okay? So in the objective, you pay proportional to these products of the width, the capacity, times the length with which you build the pipe. And so the objective is sort of like minimizing the volume of this network subject to S and T being sufficiently far apart. Okay. So that's the first thing to say. But so now actually, let's think about cuts. Right? So back when we were talking about max flows, it sure seemed like cuts mattered a lot. So let's observe that there's a connection between ST cuts and this dual linear program. So fix your favorite ST cut A comma B. So remember, the source should belong to A, the sink should belong to B. A and B partition the vertex set. So as usual, we have our 4 categories of edges. Right? Those that go forward, those that go back, and those that go internal. Okay? What I'm going to do is I'm going to show you how to take a cut and from it extract a feasible solution to that dual linear program so that the objective function value of that solution equals the capacity of the cut that we started with. So this linear program is actually encoding in it all of the ST cuts of the graph along with their capacities. Okay, so you gave me the cut. I'm going to give you back a feasible solution to the dual. How do I do it? Well, linear programs allow you to assign fractional values, but I'm not going to bother. I'm just going to use 1s and 0s. And I'm going to do 1 for all edges sticking out of the cut. Okay, so for all edges in delta plus of A. Remember, delta plus of A are the edges sticking out. Okay, so the tail is in A, the head is outside of A. So, I claim that no matter which cut you gave me, the result is going to be a feasible solution to the dual linear program. Do you see why? So if all the lengths are either 0 or 1, what do these constraints say? These constraints say that for every single ST path, it better be the case that one of the edges it contains is one of the 1 edges. You cannot have a path which is all 0 edges. But if you gave me an ST cut, and I put 1 on every edge that goes from A to B, there's not going to be any ST path going from S to T that doesn't cross this cut. Okay? So by putting a 1 everywhere across a cut going from left to right, I actually put a 1 on every single ST path. So that's why it's feasible. What's the objective function? Well, let's just plug in. So all the zeros drop out. We're left with just the 1 edges, and those are the edges sticking out of the source side of the cut. LE here is 1, so I just get the capacity. This is certainly a quantity you're familiar with. This is just the capacity of A comma B. So from every ST cut, I can extract a feasible solution to the dual with objective function value exactly the same, equal to the capacity of the cut. Okay? So let's put this together. So what have we learned? So we have our flow network. We can think about the value of the maximum flow, whatever it is. We argued, or on exercise set 4, you'll argue that the optimal solution to our linear program is exactly the max flow value. So this is just because we have an LP formulation. Let me stack these under each other. Let's do it this way. This is at most the optimal solution of the dual linear program. Why? Well, remember, this is the meaning of a dual. Okay? Every feasible solution to the dual provides an upper bound on the best possible objective function value in the primal. Okay? So it's what we said was by construction. Okay? This is also known as weak duality. Okay? But the point is, by definition of a dual, this holds. Finally, only bigger than this is the min cut value. Okay? So why is this true? Why can this quantity only be bigger than this quantity? Well, think about this dual linear program. It's minimizing. It's trying to make something as small as possible. Cuts correspond to a special case of the feasible solutions of the dual linear program. The min cut value is the best objective function of one of these special types of feasible solutions. The dual linear program can optimize over all feasible solutions, not just those corresponding to cuts. Since it's minimizing over a bigger set, it can only come up with a smaller number. Okay? So the dual linear programming optimal solution is not going to be any bigger than the min cut value. Okay? So is everyone with me so far? Okay. So again, this is weak duality. This is because the dual optimizes over a superset of feasible solutions compared to the cuts. All right. So cool. So this says that the value of any flow is upper bounded by the value of any cut. Okay, we knew that. We proved that back in lecture 1, maybe lecture 2. And actually, now that we're in lecture 8 of 261 and we're smarter than we were before, we know something actually much stronger than this is true. And we even know how to prove it. Okay? When we proved the correctness of the Ford-Fulkerson algorithm in lecture 2, what did we show? We showed that the algorithm is guaranteed to terminate, and it will hand you on the one hand a flow, on the other hand a cut, so that the value of the flow equals the value of the cut, proving simultaneously their respective optimality. Okay? So Ford-Fulkerson tells us for every graph, the left-hand side is equal to the right-hand side. Okay? Which means, of course, we have equalities throughout this chain of inequalities. Okay? So by max flow, min cut, equalities hold. So in fact, we can strengthen this to say equal. We can strengthen this to say equal. Okay? So you've seen a full proof of all of these facts. Okay? So if there's some step which isn't clear, let me know. So we use today's machinery, just the definition of a dual, to argue the weak direction, that the max flow can't be bigger than the min cut, and then we're just invoking what we did at the beginning of the class to know that equality holds. So why is it interesting that equality holds? Well, there's two reasons this is interesting. Each of these is interesting. Let's start with the first one. Okay? The first one saying that the optimal solution to the primal linear program actually equals the optimal objective function value of the dual linear solution. Why is that interesting? Well, we observe that by definition of the dual, we have this inequality. Okay? The dual optimal can't be any smaller than the primal optimum. And remember, the dual is trying to get the best upper bound of this very limited form, where we take these linear combinations of the constraints in the primal. So that's fine. The dual is the best possible upper bound. But the question is, how good an upper bound is it? Now, in our toy example, we actually came up with a dual solution with value 5/7 equal to a primal solution. So they both had to be optimal. But that was just one toy example. Okay? But we proved so-called strong duality for our toy example, that the optimal solutions are equal. There is no gap. And so we're interested in understanding, when is there no gap? Okay? So that's called strong duality. That'll be the main subject of Tuesday. But so this first equation is proving a special case of strong duality. Okay? It's saying, if you consider the linear programs corresponding to max flow problems and the corresponding duals, for those particular primal dual pairs, there is never a gap between the optimal objective function values. They are always equal, never a gap. Okay? We'll see that's true for general linear programs, but we're now seeing that it's true in a special case, these particular primal dual pairs. So that's why the first equation is interesting. It gives us linear programs with no gap between the primal and dual optima. How about the second equality? Why is this second equality interesting? Well, if you think about it, if I told you I was going to solve the ST cut problem by linear programming, it actually doesn't seem to type check. It seems kind of weird, actually, right? Because what's a cut? You make a hard binary decision for each vertex. Is it on the left or is it on the right? So really, it's kind of like you want to assign each vertex to 0 or 1. Linear programs, on the other hand, by definition, can use fractions. Right? By definition, the variables are just any real number, and then you take the intersection with half spaces, which maybe like bring them down into an interval. But you certainly cannot encode integrality constraints into a linear program. Okay? So in general, you have fractions with linear programs. So how is it you could solve this linear program with all this fractional stuff and make use of it to compute a cut, which doesn't feel fractional at all? So what this second equation says, it says for this particular linear program, okay, for which cuts are a special case, actually fractions aren't helpful. So what is this? This says, what's the optimal value of this solution if I only use cuts, 0, 1 solutions? This says, what's the optimal solution to this linear program if I'm also allowed to use fractions? And having an equation here says it doesn't matter. Or put differently, for any fractional solution, I can come up with an integer solution, a cut, which is just as good. So the takeaway here is that while in general linear programs have fractions, there are some important and natural linear programs where, despite the fact in principle you could get fractions, there's always an optimal solution, which is 0, 1. Okay? Questions? Yep.
So we showed that the optimal value of D is equal to the minimum cut value.
Yep.
But how do we know that the solution itself, the values of LE, they themselves are integers and fractions?
That's a good point. So the question was, so certainly I showed you that there exists some solution, which is 0, 1. Namely, take the minimum cut and run this argument. Okay, so then I'll get a 0, 1 solution whose objective function value equals the min cut value, and therefore equals the optimal objective function value for any solution. I'm not claiming there can't be other equally good fractional solutions, but there's always going to be one optimal solution, which is 0, 1. And that follows from this argument. Other questions? That's a good question. Yep?
But don't all optimal solutions have to have that form because the solution has to be at an extreme point?
Okay, so good question. So this is, so the question was about extreme points. So those are the vertices or the corners of the feasible region. And it's definitely true that there always will exist an optimal solution at one of these corners. And you're right that for this particular feasible region, those corners are going to be 0, 1. You might get like a weird edge case tie, where kind of there's an entire face, a entire side, if you like, of the feasible region, which all has the same objective function value. So then if I take something from the middle of the side, that will have fractional coordinates. But you're absolutely right that if you restrict yourself to the corners, and every linear programming algorithm you might ever use is going to hand you back a corner, hand you back a vertex, then it's guaranteed to be 0, 1. Yeah, good question. Other questions? Yeah.
Do we not know the max flow min-cut theorem in advance? I guess that's sort of what he just asked. Would that be a reasonable thing to even guess that the integer values are in the same optimal solution?
That's a good question. You could hope, you could cross your fingers. I mean, basically, whenever you have a problem which you know is polynomial time solvable, it's reason to hope that there might be a linear program which solves to 0, 1. Okay, so once you know it's tractable, you know, maybe there's a natural LP which proves that it's tractable. So it's sort of like if you saw, you know, if you already knew Edmonds Karp, for example, you could imagine sort of guessing this. Of course, then you know the max flow min-cut theorem, but you get my point. So it's a little bit circular because often, you know, in solving, you know, and I'll show you more examples. In solving these problems, you often wind up kind of proving strong duality for a primal dual pair as a byproduct, because that's how you knew you were optimal. Okay. Good. Other questions? Good questions. Okay. And again, just to sort of tie this into earlier themes, so I kept asking you over and over again every time we studied a new problem, how do we know when we're done? Given a perfect matching, how do we know if it's minimum cost? Given a flow, how do we know if it's maximum? And in some sense, LP duality is like the ultimate version of the answer to this question of how do we know when we're done, okay? So that's sort of one way to think about it. All right, so what I want to do next, so I've only showed you how to take the dual of one particular type of linear program. Linear programs which are of the form max C transpose X, subject to AX at most B, and X non-negative. There's other forms of linear programs. You might have a minimization objective, you might have equality constraints, you might have unconstrained variables that can be negative. Now, we've talked through the cases like, well, all of these things can be converted to each other. So if you wanted to take the dual of one of these other types of linear programs, you could convert it using those tricks to the form we've already handled and take the dual, which we know how to do. And that's fine. That's totally legit. It turns out to be more convenient to just have, at least for our purposes, to have a general recipe. So for no matter what form of a linear program is in, I'm going to tell you the recipe for how you derive the dual. Okay? So here's the recipe for duality. Okay? So suppose you have a primal constraint with n variables and m constraints. So we know, so just like before, so the first several things I'll say are just like before. In the dual, there's a multiplier for each constraint. So there's going to be m decision variables, y1 up to ym. And over here, there's going to be one constraint for each of the variables. So for each of the coefficients in the objective function. So n constraints. If you have, so for the moment, let me just focus on maximization linear programs. So as we saw, when you take the dual, you exchange the right-hand side in the objective. And also you flip max to min. Okay? This is going to be min, B transpose Y, right-hand side equals C. Okay? And we know that the constraint matrix gets transposed. Okay. So all that we already knew. So now there's a few little bells and whistles I just want to tell you about, again, depending on if you have equality constraints, unconstrained variables, and so on. So if the ith constraint is, well, what do we already handle? Okay, so far we handled less than or equal to constraints, and we argued that each one of these should give rise to a non-negative dual variable, yi. Okay, so it's just like what we had before. If this goes the other direction, then we're going to get a non-positive dual variable. And if this is an equation constraint, then we're going to get an unrestricted random variable. Meaning, sorry, not random variable, decision variable. Meaning it can take on both positive and negative values. Okay? So these two we didn't see yet. We'll see in a second. This is what we saw. Okay? But this is the rest of the recipe. And then similarly, whenever you have a non-negative variable over here, so this is like in the case we talked about, then we know we're going to get a greater than or equal to constraint. Right? That was the greater than or equal to C that we had all lecture. So this is going to be greater than constraint. And then you can guess what's up with the rest. So if it's non-positive, then you get a less than or equal to constraint, and if it's unrestricted, positive or negative, then you get an equality constraint. Okay? So is it clear what I mean by this recipe? So the details are just, what happens, so the two things which might be different, what happens if that's an equation rather than an inequality? Then, instead of being non-negative, this is unrestricted. And if you like, you can also flip this inequality, and then you also flip this inequality. Okay? The other issue is, what if you don't have a non-negativity constraint in the primal? And that just means that the inequalities in the duals will be equality constraints. Okay? Otherwise, the formula is exactly the same. So any questions about that? So this only defines the dual linear program for maximization problems. And so we're going to define the dual for a minimization LP to just be the reverse of this operation. Okay? So if your primal linear program actually has a form like one on the right, you just follow the arrows in the opposite direction to get its dual. You'll notice that by definition, if you have a linear program and you take the dual, and you take the dual again, you'll get back to the original linear program. Okay? You just follow the arrows to the right, and then you just follow them right back left. Okay? So the dual of a dual is the original primal. So something I'm not going to prove, well, I guess one case of this will be on the exercise set. But so for all of these versions, you have weak duality. Okay, so in all cases, so if you have a maximization primal, like we did previously in lecture, its optimal objective function value will be at most that of the optimal solution to the dual. And then flipping it around, if you have a minimization dual, then its objective is going to be at least, optimal objective is at least that of the corresponding dual. Okay? So I showed you the proof. Actually, I've left the derivation. Oh, I didn't leave the derivation up. That's too bad. That's too bad. Okay. So we derive this for the one particular form of linear programs, max C transpose X, AX at most B, X non-negative. Exactly the same kind of derivation verifies a weak duality for every other linear program of all of these forms. Okay? And again, I mean, this is really just by construction. The definition of a dual linear program is defined the way that it is so that weak duality holds. The dual's meaning, so again, it's fine if you want to sort of memorize or write down this recipe, and when one is confused and when one doesn't understand a problem, it's nice to have this to fall back on and just apply the recipe. It's kind of mechanical, it always works. But do not forget the true meaning of the dual linear program, which is as a certain form of bounds on the optimal objective function value of the primal. Okay, in all cases, that's the meaning of the dual linear program. And once you realize that that's the meaning, weak duality is basically tautological. Okay? So it's basically by construction, by definition. Okay? In fact, I don't know if your math classes were like my math classes, but something the mathematicians seem to never admit in the courses I took, they would write these definitions on the board as if they like fell from the sky, as if someone like sat down at their desk and said, every open cover has a finite subcover, something like this. That's not how mathematics works, okay? Where do definitions come from? They are reverse engineered to give you the right theorems, okay? To help you understand things. So here, you start with weak duality, you reverse engineer the definition of a dual so that it is true. Okay. All right. So as I mentioned, there's this thing called strong duality, which we'll do a proof sketch of on Tuesday, which says that there's never a gap, that these inequalities always hold with equality. But actually, even just knowing weak duality, which at this point we've proved, has some really interesting corollaries. So corollary 1, suppose the primal linear program has unbounded objective function value. That is, for a maximization problem, you can have arbitrarily large objective function value. For a minimization problem, you can have arbitrarily negative objective function value. What can you immediately deduce about the dual linear program if the primal has unbounded objective function value? Good. Has to be infeasible. There can't be a solution. Why? Well, suppose there were a solution. Okay? By the definition of a dual feasible solution, it would give you a bound, a finite bound, on the best possible primal objective function value. Okay, so if there's no bound, there's no dual feasible solution. Okay? And similarly, if opt of D is unbounded, I forgot the conclusion, D infeasible. If D is unbounded, then the primal, if the dual is unbounded, then the primal has to be infeasible by the same argument. And there's a part 3 as well. So suppose you have feasible solutions to both the primal and the dual. And it's also the case that they have equal objective function value, meaning C transpose X equals B transpose Y. What has to be true about this feasible X and Y? So think back to like when we were talking about flows and cuts, right? So we deduced quite easily, and we deduced it again today, that whatever the max flow value may be, it's never going to be bigger than the minimum cut value, okay? So even if you didn't know the max flow min cut theorem, you could at least conclude from that that if I showed you a flow and I showed you a cut and they had the same value, they both have to be optimal, a maximum flow and a minimum cut. Okay? The same thing is true here. Given that we have weak duality, if I ever show you a feasible primal X, a feasible dual Y, and they have equal objective function value, that simultaneously certifies the optimality of both. So I'll draw a picture that I draw once before when we were talking about max flow min cut. That's exactly the same picture here. So if you think about, the objective function values of feasible primals is the X's, and the duals is the O's. Weak duality says all the x's are left of all of the o's. You can never have an x to the right of an o. So if I ever can show you an x and an o superimposed on each other, they got to be optimal. No x can be further to the right, because then it would be further to the right of an o, which is disallowed. No o can be further to the left, because it would be the left of an x, which is disallowed. Okay. So everyone clear on that? So even without having proved strong duality, we can at least say, if we're ever so lucky to get our grubby little hands on feasible primal and dual solutions so that the objective function values match, then we're done. We know that we're done. We've solved both problems optimally. Questions about that? Okay, so one final concept for the lecture, which is a corollary of the corollary. So this is something called the complementary slackness conditions. It's again trying to provide a generic answer of how do we know when we're done. That is, it's providing certificates of optimality. So it's going to be a corollary of part 3. Okay? So suppose x and y are again feasible for the primal and the dual. So think about like a flow and a cut if you want. And the complementary slackness conditions hold. Okay? CS is probably not the right acronym in a class like this. So complementary slackness 1. Suppose that whenever you have a decision variable in your primal with a non-zero value, okay? Whenever you have a decision variable in the primal with a non-zero value, suppose it's the case that in the dual, remember in the dual, constraints correspond to variables, so there's going to be some analogous jth constraint in the dual. Suppose that whenever xj is not 0, the jth constraint is tight. That is, it holds with equality. So jth constraint of D satisfied with equality. Yeah. And then the other condition is just the reverse. So whenever yi not equal to 0, x satisfies ith constraint with equality. Then x, y both optimal for P and D. Okay? So the point is, it's another sufficient condition for optimality. If you have a primal solution, if you have a dual solution, and these complementary slackness conditions hold, boom, you know you're done. Okay? So I'm not going to have time to give you interpretations today. We'll pick that up on Tuesday. But so for max flow, let me tell you what the complementary slackness conditions translate to. They say, suppose you can find a flow, feasible flow, and an ST cut. And suppose it's the case that every edge crossing the cut is saturated. Okay? This is fully used. And every edge going backward across the cut is 0. Those are the complementary slackness conditions. Just take it on faith for now. Those are complementary slackness for max flow. Okay? Whenever you have something crossing the cut forward, it should be fully saturated. Okay? And everything should be 0 backward. If you can find a flow and a cut that have those properties, then they're both going to be optimal. Okay? And if you look back at our proof of the correctness of Fulkerson, actually we exhibited a flow and a cut with exactly those properties. What I'll talk about in detail on Tuesday is in the Hungarian algorithm. You might remember in the Hungarian algorithm for min-cost matching, we had vertex prices. Where did those come from? Those are dual variables. We had these weird invariants with these weird reduced costs. Where did those come from? Those are just complementary slackness, okay? So you've already seen all of these concepts in more concrete guises, all right? So the proof is very short, but I'm out of time, so I'll leave that for Tuesday, and then I'll give you concrete examples to help you to help reinterpret the algorithms that we've studied in terms of the concepts of LP duality that we've learned today. See you then.